Well, let's now actually see how we can calculate line integrals. Not just talk about some basic concepts and discuss curves, but actually try and evaluate them. So you know that line integrals are important, and you'll see some examples later, but now we're just going to see methods of computing line integrals. And you have seen that there are different types of line integrals. In this course unit, we mostly focus on the integrals of vector fields. And we'll also show that they're closely related to the definite integrals. To do this, we need to have a way to express curves, and the parametric form is one of the most useful expressions here. So what you do, you take your position vector, which traces the curve, and define it as a function of the parameter, as a vector field, which depends just on one parameter in every coordinate. So you can think of you're traveling somewhere and you just time it, and at different times you'll be at different positions. That is called the path of integration sometimes, and it can be defined between 2 points, so the starting point and the end point. For example, you can start from point A and go to point B, and you do it along that curve. So that is the curve C, and there will be a parameter which tells you where you are along this curve. There might be a case where there is no end and start point, where the curve is closed, and an example will be a circle. So then you have a circle, you don't have an end and start, but you still can move, and there will be still a parameter involved, which normally varies between 0 and 2 pi. And an example will be the circle described by the x coordinate a cosine t, y coordinate a sine t, and 0 third coordinate, because say it's in a plane z equals 0. And in general, so in this particular case, the parameter t varies between the 0 and 2 pi, so you can get the full circle, but it can be anything else as well. So in general, parameter t can vary between a given limits between 0 and 2 pi, 0 pi, 0, 1, anything. So if the path is not closed or closed, you still can have a range of parameters. And as a reminder, if you vary between 0 and pi, you will get a half circle. So that will be t varying between 0 and pi in this particular case. And if you go 4 pi, that means that you move more than once round this circle. So always pay attention to the range of the parameter values on the curve. And also we have to differentiate. Why we have to differentiate? Because we need to know tangent direction. You'll see in a minute why. But in order to get a derivative, we should be able to differentiate that curve. So it has to be smooth. And it is also continuous. Sometimes it's possible to do a more general case where the curve is not necessarily smooth, but piecewise smooth. What does it mean? It means that you take several curves, each of them are smooth, and you just join them. So you have A to B, which is smooth, and B to C, which is smooth, but the whole curve has some kink in it. So that is called piecewise smooth curve. which we consider only these cases. And here comes the definition. So the line integral of a vector field, again, note here it's a vector field, a vector function, along the curve, along the path of integration, curve C, from point A to B, is defined as follows. So that is a definition that I want you to bear in mind. And you can see in this definition that it involves the path of integration from A to B for that curve. And it's important that point A is characterized by position vector A for the parameter t equals A, small a, and B characterized by the position vector with the parameter equals to B. And we can show how that in general, for any given point, we can show how we can get the tangent at every point, which is r prime. And you can notice that what we did here, we expressed our little element on the surface, that little element, which we can call dr with the direction, express it as the tangent times a little change in the parameter. And that's indeed what we have here. In general, most of the curves are not closed, but if the curves are closed, then there is an interesting notation which you write an integral with a circle around it, which indicates a closed path of integration, like a circle. So if you want to integrate something along the circle, then you use that notation.